let's just do a quick review of what we talked about yesterday. So the subsets of the proper, or the set of real numbers. So let's go down maybe and just add some examples here. You can define these for me. So the letters we apply are this. Capital R represents the set of all real numbers, but we're looking at the subsets. So what letter do you think we attach to the set of natural numbers? N. How about whole numbers? W. How about integers? Sometimes.
Z.
Sometimes it's I, but usually it's Z. It could be I, capital I. But usually we do Z. Rational numbers. That was a weird one.
X.
Q. Okay, and the irrational numbers, like a lot of times we won't even, they get left out because they're not related to any of these others by sets or subsets. But one way we can do this is Q prime. You see that little hash mark up there? That's called a prime. And it shows up. Something you'll see in math is that we use these symbols in different contexts. We use these symbols over and over again. So I mean, it could be confusing, except in the context, it's always pretty clear what we're doing. Like in calculus, for example, in a couple of years, prime is, we're going to use that one a ton, but it means something different than this. It means derivative. Take the derivative of a function. We'll get there in a couple of years. So examples. Let's start with, well, just somebody pick one. Which one you want to do? Natural numbers. How do we define the set of natural numbers? If we use our set notation, what's included in that?
1,
2, 3, etc. Right? Same pattern. Okay, whole numbers, what's that add?
0.
Good. Integers? Okay, now so this time we've got to include all the negative natural numbers, right? So this list is going to extend forever in the negative and positive directions along the real line of the number line, right? So we're going to have this pattern where we go from negative infinity up to -3, -2, -1. 0 separates the negatives from the positives, and then 1, 2, 3, something like that, right? Okay. Is that weird to say from negative infinity? That's how we talk about it in math. Mathematician would say this is going to be the set that extends all the hashes on a number line from negative infinity all the way up to positive infinity. It's a little weird to say something that way because it almost implies that you can get there. Can you? No. Infinity is not a number. Rational numbers. How about that one? So we've got the set of what? Remember this one? The set of what? Now it's going to tell us the next thing we should see is the set of what? Okay, so we said, I heard it, the set of fractions of the form m over n, such that or when or where, we've got that conditional bar, you recall that, such that what? Are both integers, right? Okay, I'm going to give you another shortcut for saying that. This is another one. If you want some more stuff with this honors class. So we could say m, and that's kind of a weird sideways e, and that's how you draw it. It's got to be kind of like a half circle, and then with, it's kind of like half of a circle with a diameter drawn through. You just cover up the right half. Okay, what that means is an element of. And you see that symbol. So m is an element of, what am I going to put there? You told me m is an integer and n is an integer. So how can I make this really brief and concise like we like to do in math? M is an element of, how do I say it instead of integers? Z. Okay, good. So m is an element of z. Okay, here's another one. It's kind of a weird one. You know what that symbol means in math? And I don't expect you to remember, but I'll do this over and over again, and within a week or so, you'll just, it's like learning a language, you just get it. This means in math, and, it's a logical and symbol. So you see that a lot in programming or in math. And, what do I have to say about n? Say it again? Does not equal 0. What else about n? What else about n? Is an element of z, okay? And I could have probably said m comma n is an element of z, and maybe even made it shorter, but I didn't, so. And what else? Yeah, I heard somebody say it. N is not equal to 0, so I need another condition there. Oops, that's bad. Okay. Now, this is an and statement. We haven't used it on this page, but can anybody guess what that means in math? Or, yep. Okay, we'll talk more about this throughout the year, but there's a big difference between an and an or, isn't there? Okay. So, if I were to say all the students in this class, just make a quick point of this. All the students in this class that are, let's say, you want the set of everybody that is a student in this class and is a girl. Okay, that's going to be just, what's that going to be? Raise your hand if that includes you. Okay, good. What if I said the list of students in this class that are, or I want all the people that are either students in this class or a girl. Raise your hand. Everybody. See the difference? Okay. And is more exclusive. We talk about and I'll just write this down. You know, once again, this is probably not something I do with all the classes, but with you guys, I'm going to. So we'd say, we already said that equals and. That's what we call a conjunctive statement in math. Okay, and we refer to that as it's the same thing as saying an intersection. Okay, so for example, let me draw a picture for you. So if we did something like this is the set of all students. And let's see. Okay, yeah, this is the set of, we'll just assume room 304 girls. Then we want the intersection of those two. We want the only part that's going to be a part of both of those at the same time if we're saying and. Right? So think about, like if this one were blue, and this one were red. Oops, that's not red. We want the part that's overlapped, the part that overlaps to make purple, right? So this is the part we're talking about right here. It is double shaded, right? Now what if we made instead, if we wanted an or statement? That's not an intersection, right? We're talking about an or statement. That's what we call a, I said, hang on, did I say that backwards? Mix this up. I did, this is supposed to be disjunctive. It doesn't really matter, you're never going to say those words. And this is conjunctive. You won't say those for a long time anyway. I think that's right, yeah. So this is not going to be an intersection, right? This is everything combined. Okay, this is what we call a union. So it's all the stuff combined. It doesn't have to be double shaded. So if we go back to this picture, now it's just the whole thing. Anything that is either shaded blue or shaded red gets included. So if we have sets, maybe I'll think of just a different kind of abstract set. So if we've got a blue set, and we've got a red set, what's going to be the union of those two sets? So an OR statement. Both, everything in both. If I'm talking about an AND statement, which is an intersection, that's only going to be that little spot in the middle, right? Okay? You probably talked about that a little bit. All right, so we got rational numbers. Now what about irrational numbers? How are we going to do that one? Okay, good. So let's go back to our set notation. So it's the set of, I think the letter we used was H last time, not that it matters. The set of H such that H is not a rational number. So let's use our new fancy math notation for that. How do you think we might do that? I'll give you a hint. How do you say not equal to? You take an equal sign, and what do you do to it? Put a slash through it. So that's the negation of equals, it's not equals, right? So what do you think you're going to do here? Is not, but not, what's that mean? It's not an equal sign, it's not an element of them, right? You want to say not an element of, so we'll do that. It's not an element of what? Q of Q, right? Okay, does that make sense? So a mathematician would, did I say something wrong there? Oh, yep, you're right. You're right, it should be. Let's do this. Can I just grab off the way? Oh, man. You'll get lots of comic relief from me stumbling around up here all year. I do it quite often.
You said still.
I got to erase. Oh, here, I'll just do this. I'll just sneak a little H in there. How's that? I tell you. So a mathematician would say the set of all H such that H is not an element of Q. Okay? That make sense? Okay, sort of.
Is there a sign for set? Like
That's it, set notation.
you put not set of Q?
Nah, there might be some weird permutation of a way to do that, but this is how basically people would do it. Yeah. Question?
So what does H represent?
So H is just, we're defining, H is what populates this set. So Q prime is the set of all H. What the heck is H? Well, that's H. H is just not an element of Q. Okay, and we're assuming here for all these that we're talking about real numbers. So that's already, we're assuming from the very beginning that everything in here that we define is some kind of real number. Okay? Okay, other questions? All right. So we got all that stuff in there. Now here's the next thing I want you to think about. I don't really like this Venn diagram very well, honestly. In fact, cross it out. And we're going to make a different one. I'm going to go back and use this one instead. This is better. And we'll talk about why here in a second. You can tell me when we're done how come this is superior to the one that's on that green sheet. So our goal here is we want to create what's called a Venn diagram. Have you heard those words before? Sometimes they're called set diagrams, named after Mr. Ben. Not sure what his first name was or who the heck this guy was, but he's the guy that first came up with this schema for representing sets visually. It works really well though. So we want to add the symbols, and I guess on this one we got I for integers. Oh well, we thought of it as Z before. Usually it's Z, but where I pulled this, the graphic I pulled this from, they used I. So we want to label each of the appropriate sets with these letters, okay? What do you think? Can somebody tell me where one of those is gonna go? We got all the letters, I instead of Z, but everything we just talked about, representing these subsets of the set of real numbers. Can you tell me where one of those should go? Okay, N's gonna be the small circle or ellipse, whatever it is, the small set, right? How come it's the smallest? Okay, good, it's the smallest subset, isn't it? Everything else includes, all the other ones, except for Q prime, include N. Say it again.
Smallest infinite.
Smallest infinite set, I know, it's a weird thing to say, but it's the smallest infinite set. So that's gonna go there, right? Okay, instead of, we know what that looks like. What's another one? W, okay, good. We know W is gonna go there. W includes N, but we get this one additional element that N doesn't have. What else? Okay, integers. Come on, there we go. So the integers, now we include everything that's included in here, but this is the extra stuff that's only exclusive to this set, not in the subsets, right? What's next? Q. Okay, that makes sense, doesn't it? Right, because all this other stuff, the integers are a subset of rational numbers, but then there's some extra, in general, what would all those extras look like that are in the set of rational numbers but not included as integers? Give me an example. 1/2, so you said, it's another one. 1/3, etc. Right, fractions that don't reduce to integers, okay? And now, here's the part we gotta be careful with. What about Q prime? Where's that gonna go?
Outside of the circle.
Okay, it's gonna go outside the circle, isn't it? It has to go outside because it's separate from, come on, there we go. It's separate from the set of Q, right, the set of rational numbers. They're mutually exclusive. That's another word we use in math, they're mutually exclusive. You can't be one and the other, you have to be one or the other, right? Okay? So why is that maybe a better Venn diagram than that one? If we could put the letters there, that would be N, W, Z, or I, Q. And if this whole thing's a set of real numbers. What do you think? I mean, it's not a big deal, but something about this offends me. Yes, sir?
Because maybe that box around it makes you think that they're all.
Ah, okay, it makes you think that there could be some other things in there that aren't included in the set of rationals or irrationals, right? Exactly. That's my problem. Okay. If we did add these in there, though, if you want to fill this in, I mean, obviously, we know what this would be. N, W, I, Q, Q prime, right? And then what would this whole set be called up here? I guess we could do this. Reals. So that's an R. Okay. All right, so I'm going to move on. You guys, let's just do like 2 of these. And that's all. If I wanted you to name all of the sets to which, let's take number 1, -10 applies. And let's just use their symbols.
Z.
Say it again.
Z.
So it's in Z. Okay, what else? So if it's in Z, it's in Q, right? What else? If we included one more, I'm kind of cheating on this one. R, yep. Okay, how about 4? Okay, so it's definitely Q. Any others? R, okay, I'll put the R there. How about, we'll go the other direction this time. I, okay, it doesn't look like I, but if I simplify it, it is, right? 24/8 is 3. If it's I, it's also W. And say it again, N. There you go, okay. Actually, it doesn't necessarily, if it's in I, it doesn't necessarily have to be these, but in this case it is, right? So the way we would have probably thought about this up until, I mean, we would have probably said, okay, what's the most exclusive set that's in? Does this logic make sense to you? The most exclusive or the smallest subset it's in is N, so all the others have to be included except Q prime, right? Because they all contain N. Okay, how about number 9? Okay, so that's really, oh, we forgot, oh, I know we did put R. What about this one?
Q and R.
Q and R, that's it, isn't it? Right? The smallest subset that this is in would be Q. It's not an integer, is it? Right? So all we could say here is Q and R. Okay? Make sense? What about 3? This is something we would never do. So that's like grade school, maybe, I don't know, not even middle school stuff, really. We would never use our mixed numbers, right? We'd always write that as an improper fraction. So that is a fraction, but it's not an integer, right? So what's this one gonna be? Q, and then R. Number 2, one last one. Q prime, isn't it, right? Because that's a square root of something that's not a perfect square. So we're gonna be stuck when we simplify that with a square root that doesn't go away, right? Any square root that doesn't go away, like the square root of 9 would be 3, right? This one doesn't go away, so we know we're stuck with an irrational number. So this is just gonna be Q prime and R, okay? All right, so you can, yeah, it's probably enough for that stuff. Let's talk about properties real quick. Okay, this will be a quick one. Quick review. It's been a while since you maybe have done this stuff, but we're the properties of equality for real numbers. Okay. Okay, so what about these? In some cases, things that we do in math require a certain order, but sometimes there's some symmetry involved where we don't have to do that. Now, symmetry is a word we're going to come back to a lot. Symmetry is a word we use in math and in physics all the time. Give me an example of something that has some symmetry. Face has bilateral symmetry, right? You split it down the middle, the left half and the right half are mirror images. Okay, so that's folding symmetry. What's a geometric shape that has some symmetry? Square. Square has some symmetry, doesn't it? Like if we took a isosceles triangle, right? If we took, let's just take a square as an example. Right on this one. No, I can't. That's all right. So if I take a square, how could I reflect it on itself? We'll make blue lines. How many blue lines could I make so this reflects perfectly on itself? I'm hearing lots of them. What's one? Okay, I saw the vertical line through the center. Another one. Horizontal. Any others? And then the 2 diagonals, so I get 4. Okay, so that's what we call line symmetry, or all kinds of ways you can say it. Line symmetry, because the line is the part that you have symmetry about. Could be reflective symmetry. You could think of it as, as reflecting it over the line. Or it could be, what's the other one we say? Folding symmetry. Okay. There's another type of symmetry. What else could I do you think, to this square so it has some symmetry? I could rotate it, sure. Okay. If I put a tack right in the center of that square, how many degrees would I have to rotate that thing before it looks exactly the same as it was before? 90. Okay, and then I could go another 90, right? Okay. So everybody sees we get these different kinds of symmetry. That's geometrical symmetry. There's some other weird kinds of symmetry too. Time symmetry, physics. Yeah, I got one for you. This is kind of weird. If you, let's say you filmed me tossing a ball up in the air, and you're going to start the film right when it leaves my hand, and you're going to stop it when the ball gets up to the apex and projects right to the very top. Okay. If I ran that video backwards, what would it look like? It looked like the ball returning to my hand. In fact, would you even know if I'd run it backwards, or would you maybe think that I just filmed the whole trajectory? You didn't get anything, right? You couldn't tell them apart. So we say there's some time symmetry. You can either run the time forward or backward from the apex, and it's going to give you the same result, right? Physics works backwards most of the time. It's really weird. So there's all kinds of symmetries you maybe never thought about. I could give you some even way more bizarre ones that you have to hold on to your head because you might make your head explode. for now, we'll just leave it at that. But here's some other kinds of mathematical symmetry. These properties, see if you can think about this in terms of symmetry. The commutative properties. Remember what that one is? Commutative property of addition and multiplication. Somebody raise your hand and help me out here. What's the commutative property of addition? A plus B equals B plus A. How about multiplication? A times B equals B times A. So you're familiar with these, you remember them. Okay, there they are, right? How can we use A's and B's instead of numbers, obviously? More fun?
You don't have to do, you don't have to.
Okay, you're not constrained, it's more general. We want to be as general as we can with math, right? We want to be able to apply in all situations. So here's a way to remember this. I think a good way to remember this. When a person commutes from home to work, what do? Go from home to work, right? They change places, don't they? And at the end of the day, workday, they commute back from work to home. So commute just means to exchange, right? So here, when we commute a sum, we're just flipping it around. We're just exchanging the parts. Same thing with multiplication. What about subtraction? Does it work for subtraction? Oh, it doesn't, does it? Doesn't work for subtraction. So if we try to, it works fine, obviously, for addition and multiplication, but if I try it with subtraction, I get different results. 17 minus 5 is not the same as 5 minus 17. What about division? That can work. 20 divided by 5 is not equal to 5 divided by 20. So you cannot commute subtraction and division. Okay? What about the associative property? So we got the associative property. What's it mean to associate? People you associate with are people what? Say it again. Ideas? But what's it mean to associate? Say it again. Connect things, kind of. Like if, sort of. I mean, the people you associate with are the people that you sort of group yourself with, right? Okay. If there's a law associates in a law firm. They're the attorneys who have grouped themselves together into one law firm, right? So the associative property just tells us that we can group things in any order we want to, whether it's multiplication or addition. But I want to make an important point here. This might seem like a trivial point, but it's not. It's important. When you multiply things together, you must multiply things in pairs. It's not, you can't do this all at once. If I want to multiply 3 times 4 times 5, I must make a choice. I can't do the product of all 3 of those things at once. I have to do it in steps, right? Multiply in pairs. So what's one option? Probably the most obvious one that we would typically do. 3 times 4 is 12. Next step, 12 times 5 is 60. Don't have to do that though. I could say 4 times 5 is 20. 3 times 20 is 60, right? You're free to group those in any order you want to, but you must multiply in pairs, 2 at a time. Same with addition, okay? And you can also group those. Do you think this is going to work for subtraction or division? No, not going to work. It makes a difference if I group, if I've got the 3 numbers 15 and -9 and 23, I'm adding those. If I group the first 2, I'm going to get a different result than I do if I group the second 2 first, right? Same for division. Okay. If I'm dividing all 3 of these out, it makes a big difference if I divide the second 2 first or the first 2 first, right? So you've seen a pattern here. All these fancy symmetric properties that work for addition and multiplication don't work for subtraction and division. Okay. Next, distributive property. Distributive property, that's one you're more familiar with. You do it all the time, right? Everybody knows how to distribute. There's one common mistake I'll just point out here, and that is that you must distribute. When you distribute, you have to do multiplication over addition. Okay, so in other words, the multiplication has to be outside of the grouping. And this probably makes perfect sense to you, but you can't do the opposite. Like this wouldn't make sense. 6 plus 3 times 5, you don't distribute, do you? You would never distribute, add 6 to both of those and then multiply. What's one way you could defend why you wouldn't do that? And explain this to somebody younger. How would you explain it to them? What do you think?
If the 3 and the 5 are in the parentheses, that means that they get multiplied and added to 6.
Okay, why do they get multiplied first?
Because
PEMDAS, yeah, order of operations, right? You'd have to multiply, you'd have to deal with the parentheses first, right? Before you do anything else. And inside the parentheses here, we've got this multiplication. So I'd have to take care of that before I add the 6. Now up here, it's different, right? Up here, I could add those together if I wanted to, if it's possible to do. But if it's not, then I would do the multiplication before I would, does that make sense? So you're just following PEMDAS, okay? All right. So I want to draw your attention to just one quick example that illustrates that. So we could use plain old order of operations. We're going to talk more about that real soon. I could do the parentheses first, right? And I could get 12 minus 8 and get my answer of 4. Okay? That works fine. That'd be the easiest way to do it. Now, what if, though, I can't combine the stuff into parentheses? What if I wanted to do something like this? Okay, I'd have to distribute the negative, right? Does that make sense? Probably what almost everybody would have said is distribute the negative, and that's correct. But what are you really doing when you're distributing a negative? Okay, good. You're multiplying by negative 1. Good. So we could think of this as being the same as 12 plus negative 1 times the quantity x plus 3. When I say the quantity in math, what do I mean? Parentheses, yeah, right. Stuff that's grouped together. So then I would distribute the negative 1, and if I, this is, we can take a shortcut here, an algebraic shortcut, but technically what we're doing is we're saying 12 plus, if I distribute the negative 1, I get a negative x plus a negative 3, then I just combine like terms. Right? It's easier to just distribute the negative. You're right, that's our shortcut, it works. If I just distribute the negative instead, I get 12 minus x minus 3, same difference, right? Okay. All right, next step. So this is something I want to just focus on just a little bit. The identity properties. So what's your identity? What is that? What does it mean to talk about your identity? Who you are, right? Who you are. Somehow we're attaching some kind of values, probably not numerical values, to you as a person. That's your identity, right? So the identity properties, the way we often talk about this in math, the identity properties of addition and multiplication, those are just identifying what are the special numbers that we could apply either through addition or multiplication that preserve the identity of the original quantity, right? So it's not going to change. Its identity remains unchanged, stays the same. Obviously, what's the identity number for addition? What could I add to something and have it not change? 0. Okay, good. What's the identity number for multiplication? 1. If I multiply something by 1, it stays the same. Easy. Piece of cake. Those are probably the easiest of all the identities, right? Or of all the properties, the identity property. Something plus 0 is itself, something times 1 is itself. But that's strongly related to the next property, which is also very important, the inverse property. Now, an inverse, this is a word that gets abused in math a lot. Okay, inverse is, it's another thing that you have to use contextually. It depends on what particular topic you're discussing in math when you use the word inverse. It can have different meanings. The inverse for addition, the goal with an inverse is you want to know, fill in the blank. So A plus, you fill in the blank, equals its identity, which is 0. Okay? That's how inverse properties and identity properties are related. The inverse property just answers the question, what would I add to get the special inverse or identity number for addition? Sometimes we call it the additive identity. What would it be? A plus, say it again, negative A. What do we call that? in general? Opposite. Okay. So the additive inverse is a number's opposite. Okay. Always. For example, give us an example. Yeah, negative. Oh no, we haven't gotten that page. So we'll get there in a second. What about multiplication? A times what is equal to its special number for multiplication, which is 1. Multiplicative identity. What would you multiply a number by to get the result 1? Okay, what do you call that? Reciprocal. Yeah. 2 times what equals 1? 1/2. 7/9 times what is 1? Negative 2/3 times what is 1? Negative 3/2. Good. You're flipping the fraction. It starts negative, its reciprocal is also negative. Okay? So there it is. That seems pretty cut and dried, pretty straightforward, but I want you to just be aware, we'll come back to this discussion throughout the year. We're talking about pretty easy stuff, real numbers. Those are pretty concrete and easy to deal with. But you can use a lot of these properties as you go further in math. You can use these same properties in different contexts. Like, for example, with matrices. Have you guys ever seen a matrix before in math? You probably haven't. Okay. Matrices are a big deal. They're super important. Matrices, in a nutshell, matrices represent linear systems, but they do it in a way that's very compact, and you can do the math very easily. So matrices include, it's like a whole big table. There's lots of information in one matrix, but matrices also adhere to these same properties. You can do the same stuff with a matrix you can with a real number. There is an identity matrix that goes with any matrix. There is an inverse matrix that goes with that's a matrix that you start off with, and you can use them for both adding and multiplying matrices. So there's this whole other branch of things, whole other set of things, for which all these properties apply, but it's just more complicated. You can even go further in math, and you can do things like tensors, and there's all kinds of other more complicated mathematical structures that this stuff still applies to. Okay, so this idea you go a lot further with it. It's not always this simple. Here's a quick summary. Yeah, you guys, yes, it's on the, it'll be recorded for posterity on the video, and it'll be on the notes if you want to look at it, but you already know all this stuff. Let's take a quick look. Name the property in 14. No, 14. Distributed, right? All we did was distribute the 6 over that sum, right? No different. What about 19? It's distributive, isn't it? The properties go both ways, right? You can either distribute the 6 to both of these, or you can start on this side and undistribute the 6. Undistributing is not a very mathematical word. Remember what we call that? Do you know? No. If I extract that 6, if I divide it away from each term, what's that called? You know? Like down here. What do? We pulled that 3 out front. What? No? Factor. Yeah, we factored out a 3. Okay. We'll get into a lot more of that. All right, I think you're pretty good to go. Right. Why don't I'm going to give you, how much time we got?
3 minutes.
Oh, that's it? Oh, man. All right, so you got your homework. Purple sheets of homework. I will, what's today, Thursday? I'll collect those on Monday, how about? How about you guys have had a great week. Take Monday off. I'll collect them on Tuesday, right? Tomorrow we'll do something different.